Right. So day 2 of finite elements. Um, I still don't have the distribution list of emails. So what I'm going to do after class today, I'll send the stuff that you guys need to Jake, and then he'll forward it to you. So after today, you'll have some problems to work on, access to all the notes and the videos so far. All right, so last time we talked about the stress tensor. I'm going to come back to this example and do a little more with it pretty soon, but let me start today with this as like an example problem to jog your memories. Say that you have, so this matrix sigma is equal to 10, -6, 5, -6, 3, 1, 5, 1, -12, and say this is all in megapascals. So the first question is this a possible stress tensor? Okay, so what are the things that you have to think about to know whether it's possible for it to be a stress tensor? Like what? There's really only one thing that it needs. It needs to be symmetric. And this one is because those 5s match, the -6s match, and the 1s match. So this can be a stress tensor. Second, draw the infinitesimal stress cube that this represents. And feel free to, talk to each other, ask questions. You can ask me questions, but I just want to get this back in your head before we go on. So remember when I first started talking about stress, I drew that cube on the board and said it represents an infinitesimal, it represents a point, and there were components of force per area on every face. That's what I'm talking about with the stress cube. Anybody want more time to think about it? Less time? Okay, so it's a cube. You probably all figured out that part. And this tensor has a relationship with a coordinate system. So you need to decide what's going to be your, x direction, y direction, and z direction. I'm going to do it the way I did it last time. And now each of these faces is going to have a vector of force per area acting on it. which ones, so thinking back to just the definition of the stress tensor, what are the values in this stress tensor that refer to the positive x face of this cube? Yeah, so this right here is the x face. This is the y face. And this is the z face. So looking at the x face, we have 10 megapascals acting in the x direction. It's positive, so it's in the direction of the positive x direction. In the direction of y, we have -6, so that means it's in the negative y direction. You can write it. Don't do a double negative like I was about to do. So you can either do it upwards and write it as -6 or downwards as +6. Okay. And then in the z direction, +5. And now on the y face, in the x direction, -6. So that's this way. In the y direction, +3. And in the z direction, +1. Yep, thank you. And then on the z face, in the x direction, +5, y direction, +1, and z direction, -12, or else that's +12 going in. Okay. Looking at these now, it's, remember the all of the stress values coming perpendicularly out of the face are the normal stresses. So the 3 and the 10 and the 12 are normal stresses. All the ones parallel to the faces are shear stresses. And the stress, the force per area on each face is called the traction on that face. Okay. And so now I'm going to talk a little bit about traction. This is the relationship between the stress tensor and tractions is a really important thing for coming up with boundary conditions. Okay, so traction. The stress tensor can be used to find traction on a face with any orientation. So notice that directly what this stress tensor tells us is the traction on a face normal to the x-axis, the traction on a face normal to the y-axis, and a traction on a face normal to the z-axis. But we can also use it for faces that aren't at those orthogonal orientations. And the way you do that is define a face by its outward facing unit normal vector n, so n hat, that says that that's normalized, that's a unit vector. If you do that, then t that's the traction vector on the chosen face is equal to the stress tensor times that unit normal vector. Is everybody here familiar with matrix multiplications and multiplying a matrix by a vector? Anybody want a reminder about that or anything? I guess I'll do a couple example problems right now, and you can probably figure it out from that. But okay, so for example, if you have a stress tensor that's equal to 10, -5, 8, -5, 0, 2, 8, 2, -5. Is that a possible stress tensor, first of all? Yep, it's symmetric. Yep. Yeah, there's really only one thing you have to check. It just has to be symmetric. So xy has to equal yx, xz has to equal zx, and yz has to equal zy. And the diagonals can be anything. Oh, what? Sign matters, yep. So if this is the stress tensor, what's the traction vector on this face? So say this angle is 45 degrees, and this is our outward normal, okay? And using that same coordinate system, where this is in the xy plane. Okay, so how would you calculate the traction on this face? Well, you'd have to come up with a representation of that normal vector. Can you do that off the top of your head? Here's the easiest way to do it, I think. We did this a lot in dynamics, so the people who didn't understand it then get a second chance. So start at the positive x-axis, and then we're just going to keep moving around in directions to come up with the angle. Okay, so, and we know it's going to be cosine of whatever final angle we get, sine of whatever angle we get. So I'm going to start at the positive x, rotate to here. So now we're in this orientation. What's the angle I have to rotate to get to here? 135. And then we have to go clockwise 90, so subtract 90 from that. And that tells us that this is at 45. So that unit normal is going to be cosine of 45 sine of 45. Okay? So just like that. Boop, boop, boop. It's a little smart. But don't make the sound effects. Okay, so that unit normal is cosine of 45 degrees, sine of 45 degrees. So that's 0.7071, 0.7071. And what's the z component? This is in a plane, so the z component is 0. So really I should, since all of these calculations are in 3D, I need to include that always. Okay, so the traction on that face then is the stress tensor times that unit normal and if you do that calculation, you get 3.54, negative 3.54, 7.071. Any questions about that? How many people in here have Texas Instruments graphing calculators? Pretty much everyone. So if you haven't done it before, those calculators make it really easy to do matrix and vector calculations. So let me know if you want to know how to do that. Actually, the people who took deform from me, remember I gave out that list of functions you can program in to your calculators. So maybe I'll include that too, because it's a nice little toolbox to have. And then of course, MATLAB makes this really easy. So you can always just go into MATLAB and do these calculations.
What calculator will we need for this class?
You don't need anything, but I suppose I use a TI-89, and if you're in the market for a calculator, that's a good one, I think, because it does eigenvectors and eigenvalues. And we'll actually talk about that today. It's nice to have that in your pocket, you know. So you can use this relationship, this traction stress tensor relationship, to relate stress at boundaries to the applied load. As long as you know a normal to the boundary. So let me do another example where, so this is the way it is most useful in elasticity problems. So let's say that you have a problem, you know, this is a pretty typical looking problem that you would do in deform. You have a pin joint at the left, a roller at the right, and a distributed load. Now, most of the time, and most of the time in statics and deform and dynamics, when you've seen distributed loads, you see it as like a load per length, newtons per length. And you could translate that if you knew the thickness into the page into newtons per area, right, into force per area. I'm going to give this in force per area because when we're doing this kind of problems, we're sort of always forced to think in 3 dimensions, okay? So I'm going to give this external load as 15,000 newtons per meter squared, or 15,000 pascals. It wouldn't be very hard to go back and forth between this value and the value per length. But notice it is different, I guess, than what you've seen often. And the question is, so if you're trying to do a differential equation, which is what we're going to come up with as an elasticity equation, what do you need to know at the boundaries? What are the boundary conditions? Basically speaking, what do the boundary conditions do? That's sort of a vague question, but what the boundary conditions do is they limit the possible values that you can have. In our case, they limit the possible stress values at the boundary, okay? Ideally, they tell you exactly what those are going to be, but it doesn't have to be that. It can just tell you, limit the possibilities at the boundary. So in this case, if we were going to do this as a differential equation, the question would be, what do we know about the stress along the top of the beam, the top surface of that beam? Okay, so using that traction idea, we don't know anything about the stress yet, right? That wasn't given in this problem, but we know the form of it is sigma xx, xy, xz, xy, yy, yz, xz, yz, zz. And do we know, so we're trying to figure out something at this top surface. What's an outward facing normal to that top surface? Well, we actually know that it's just in the positive y direction because we know the orientation of this thing. And so if it's in the y direction and it's a unit vector, it's just going to be 0, 1, 0. Okay? So 0, 1, 0. Oh, yeah, but I'm just taking advantage of the symmetry. You're right about that. So because it's symmetric, I just made that substitution, and the same thing with this and this. And so what you have here is the stress tensor in terms of only 6 independent values, which is what you have since it's symmetric. Okay, and this has to be equal to the traction on that top surface. Do we know anything about the traction? That's right, and that's right. So that's what this is on the left, and the actual value of the traction is this distributed load. Okay, this is the so this in the negative y direction, 15,000 is the value of the force per area on that surface. That's like a definition of the traction. Okay. So I'm going to write this as 0, negative 15,000, 0. And now do this multiplication, and what it says is sigma xy is equal to 0. Sigma yy is equal to negative 15,000. And sigma yz is equal to 0. Do you follow what I'm saying about that? And then, so now we didn't learn all the stress values at the surface, but we did reduce the number of unknowns we have. And that's what you're trying to do with your boundary conditions. Let me give you one to do. So same idea. Let's say that actually, let me draw this facing the other direction. Okay, so say we have this object and we don't know anything about what's going on the right side of it. But say that on the left side, we have a distributed load of 50,000 pascals. And our coordinate system is oriented like this. Again. And the question again is, what do we know about the stress tensor on that right-hand surface? Okay, so take a minute and try to work through that calculation the same way that I did in that last example. And, you know, talk to each other about it, compare as you go. Feel free to ask questions. So this is supposed to be the solid. So if you're doing an outward facing normal to that, it's going to the left of the page. Okay. Anybody want more time? Okay, so the stress tensor starts out totally unknown again. What's the outward facing normal? -1, 0, 0, because outward from this object is going to the left. You see that? So -1, 0, 0. And then what's the traction? Well, the load is going to the right, so that's going to be positive 50,000, 0, 0. So 50,000, 0, 0. And so you get that negative XX is equal to 50,000, or sigma XX is equal to negative 50,000. And then XY and XZ are both equal to 0. And those are the restrictions you know on the boundary. Question? Yeah, sure. You're always going, your normal vector is always pointing away from the material of the object. You know, so it's going out of the surface instead of from space into the surface. So in this case, since the object is this shaded part, the outward facing normal has to go to the left. So it has to be -1, 0, 0. Any other questions? Okay. So the next thing we need to talk about is principal stresses. How do you spell this kind of principle? Yeah, good job. And the idea of a principal stress is, well, first of all, any stress tensor can be looked at in any coordinate system. You know, and so a stress tensor has one value in one coordinate system, a different value in a different coordinate system, the same way vectors do. Okay? So here is a sort of surprising fact, but it is true. For any stress tensor, there is a coordinate system where all shear stresses disappear. All shear stresses are 0. In other words, the only kind of stress there is in this one coordinate system is normal stress. To solve for the principal stresses, it's an eigenvalue eigenvector problem. So this is eigenvalue eigenvector problem. So I know in circuits you've done eigenvalue calculations. I think that's true. But I think it's done, you think about it more in terms of eigenfunctions in circuits, I think, if I'm thinking about it right. Maybe that's circuits too. But how many of you guys have done eigenvalue type stuff before? Everyone's seen that before? Okay, good. Okay, well, good. Yeah, right. Well, so I'm going to go through that, so that's good. And you can actually, it's pretty easy if you think in terms of tractions to derive this eigenvalue problem. It makes good intuitive sense. If you're looking for a surface where there is only normal stress, then what's the traction on that surface? What do you know about the traction? Well, you know that the two shear components of the traction have to be 0. And so that means that you know that the traction has to be parallel to that outward normal to the surface, right? That's the only component you can have. Does that sort of make sense? If all you have is your normal traction on a given surface, then the traction has to be parallel to the unit normal. So intuitively, you need to find a face where the traction vector is perpendicular to the face, which is the same thing as saying it's parallel to the normal vector. So if you think about it that way, what you're looking for is, so here's your stress tensor. And you want to find a face where, or basically, like you want to find a normal vector, because that normal vector defines the face that you're calculating the traction on, right? So you want to find a normal, unit normal vector, nx, ny, nz, where this multiplied together, this gives you the traction, is equal to some scalar value, just some number, times that normal. So this is something parallel to that unit normal, that outward normal. So if you think about it that way, this is just an equation saying we're looking for a unit, like an outward facing normal vector, where the traction on that face is parallel to the normal. Okay? And that comes directly from the fact that all we want that traction to have is a normal component, to be perpendicular to the surface. That's like the definition of the principal stress. Okay, so to solve this, you can so let's see, think of this as this is the same thing as this. You could verify this if you want. Okay, so the stress times that outward facing normal vector has to be equal to that. If you just went through that matrix multiplication, you'd see that you end up with this. It's just another way of writing it. And now subtract the right side from both sides, and you end up with this expression. So sigma xx minus that principal stress, sigma xy, sigma xz. And then the second row is sigma xy, sigma yy minus that principal stress, sigma yz, and then sigma xz, sigma yz, and then sigma z minus the principal stress. And that times the unit normal vector has to be equal to 0. There's one solution to this that we don't care about. That is the one that you would get if you just multiplied both sides by the inverse of this matrix on the left, right? That would just tell us that all three of these components are equal to 0. That doesn't do us any good. That's not a direction, okay? So we don't want this to be invertible. So if that left side matrix is invertible, it gives us the trivial solution. That one doesn't do us any good. So we have to require that left side matrix is non-invertible. Anyone happen to remember how we can check for whether a matrix is invertible or not? Yeah, and it's you calculate the determinant and set the determinant equal to 0. So we want, yeah, the determinant that should be with an E, I think. Determinant to be equal to 0. And at least a lot of Texas Instrument calculators do determinants of matrices. MATLAB, I'm sure, does it if you just type in determinant. But the way you do it by hand is so you could think of this as it's going to be, that's not even going to be helpful for me to write this out, I don't think. It's, is it? Okay, well, how do you do a determinant of a 2 by 2 matrix? So if you have like A, B, C, D, that's a different thing. So that's the transpose you're thinking of. The determinant is A times D minus B times C. Okay, so you go this minus this. Okay. Determinant of a 3 by 3 matrix so if you, let's say you have A, B, C, D, E, F, G, H, I. Did I do that right? Good. So you go take A and cross out the row and column aligned with A, and then calculate this determinant. So that's A times E I minus F H. And now you go to B, except you have to remember to subtract the second one. So this is going to be minus B times the quantity. So DIGF, yep. And then plus C times DH minus GE. Okay. So you can imagine, you know, use this same approach for this sort of ugly matrix. What do you know about that matrix? Sorry, what do you know? What's going to be the order of the determinant of this matrix? What's going to be the highest power of that polynomial? It's going to be some kind of polynomial. If this is the variable, this is what we're trying to find, this sigma p. If it was a 2 by 2, it would be second power. This is 3 by 3, so it's going to be third power. So you're going to get a cubic polynomial after you go through all the algebra. So you'll get a cubic polynomial for sigma p. And so how many roots are you going to have? 3 roots. In other words, you'll get 3 principal stresses. And each one of those principal stresses corresponds to its own outward-facing normal vector, corresponds to its own face. The three roots of sigma p are the three principal stresses and the corresponding outward facing normal vector for each shows the direction of that face, or the orientation of that face. Here are two important things to remember about this. The first one is that the three outward-facing normal vectors and those are the eigenvectors in this eigenvalue eigenvector problem. Are mutually orthogonal which means you can use these as your new coordinate axes. So that's really convenient. So if your three eigenvalues the values that you found for sigma p are, let's say, we'll call them sigma 1, sigma 2, and sigma 3. Then the principal stress tensor is just sigma 1, sigma 2, sigma 3 on the diagonals, and no shears. So if you're trying to find the if you're trying to find a stress tensor with only principal stresses, with no shear stresses, find the three roots of that characteristic equation, find those three solutions to that determinant equation, and you can just use those as your diagonal values of the stress tensor. Any questions about that one first? And then the second one, second thing to remember is one of your principal stresses is the max normal stress, which means no matter what orientation, no matter what coordinate system you look at this stress tensor in, you can't find one with a bigger normal stress than this. One principal stress is the minimum normal stress. So I'll call the maximum one sigma 1. I'll call the minimum one sigma 2. And then there's one that's obviously in between those two. And the maximum shear stress, so again, so if you look through all the infinitely many coordinate systems that you could use to look at a given stress tensor, if you found the one that had the biggest value of shear stress, really absolute value shear stress, I should say that. That shear stress value would be sigma 1, the maximum shear stress, minus sigma 2, the minimum shear stress, divided by 2. So with this one calculation, this one principal stress calculation, you can figure out the biggest normal stress available in any coordinate system, the smallest, and by smallest I mean possibly most negative too. You know, it could be the smallest positive value or the biggest negative. So it's an actual true minimum. You know, the smallest normal stress that you can find in any coordinate system, and those two values also make it easy to figure out what the maximum shear stress would be. And all three of those are really useful things to know. Okay, so that's why that's an important calculation. All three of those things are good predictors or parts of good predictors for like how likely something is to break, and that's usually what we're trying to do with our stress calculations. Figure out the likelihood that a fracture is going to start at that point. Okay, if I had to guess, I think people are feeling a little lost on that. Like it got going maybe a little fast there at the end. Is that right? Well, so how about on Thursday, I'll make a couple example problems, and we'll just do a couple of simple problems where you get to kind of work this stuff through your brain. And I'll send all this stuff to Jake today, and so you should get all those links and files and stuff pretty soon. And
Wouldn't you use the same kind of YouTube account to update the presentations or lectures?
yeah, so I just need to give you the link. Really, if you just look for my name, you could probably find the channel. That's right. Yeah, right. Right. Yeah, right. It's not a super common name. Okay, thanks.